Let's look at the definition of a continuous function. We say that a function is continuous at a point x equal to c if the following is true. If the limit as x goes to that point c of the function equals the value of the function at that point. So this is telling us the value of the function at the exact point c agrees with the behavior of the function values for x values very near to c. Now, in order for two things to be equal, the two things have to separately exist, so we know that the function value must exist, the limit exists, and then they're both equal. So if we're ever trying to see if a function is continuous at a certain point, then we need to check if the following three things are all true. If they are all true, then it's continuous at that point. First, is the function have a value at the point c? Then establish if the limit has a value. If both of these two things are true, then you just show that the limit value that you found before equals the function value that you found before. Now, if the function is continuous at all points in its domain, then the function is just simply called continuous. If a function is not continuous at a point, then we would say it's discontinuous. So if the limit doesn't exist, or if it exists but doesn't equal the function value, then we would say that the function is discontinuous at x equals c. Now here we need to determine whether our function f of x equals 2x plus 3 is continuous at x equals 4. That means we need to check our three facts. First, we're going to see, does the function have a value at x equals 4? So we'd look at f of 4. Everywhere there's a x, we plug in 4, and we get 8 plus 3. So we get the value of the function does exist, it equals 11. All we care about here is that it exists. Now we need to establish what's the limit as x goes to 4 of our function f of x. We could make a table, but this being a straight line, we could also quickly just think about what does the graph of this function look like. It has a y-intercept of 3 and a slope of 2. And looking at this graph, we would say as our x values get closer and closer to 4 through values less than 4, we see the output values are getting closer and closer to this height, which we can find. As the input values are getting closer and closer to 4 from the right, the output values are getting closer and closer to 4, or this value. So let's find out what is this value. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the limit is the function values approach 11 as the input values approach 4. So in this case, if we're looking at the value of the limit, we know that we could create a nicely drawn table, or if the graph is simple enough, we could graph it and evaluate its limit. Now the third step is to say, look, the limit and the function value agree. So since the limit at x equals 4 equals 11, and that agrees with the function value, we would say it's continuous at x equals 4. So if you're ever asked to show whether a function is continuous at a point, check these three criteria. If they're all met, then it is continuous. Now, if our function is not continuous, it would fit into three different categories of discontinuity. So if a function is not continuous, then we say that it's discontinuous at the point. And there's three common types of discontinuities. The first one is called a removable discontinuity. Let me draw an example of that and then we'll look at the definition. In a removable discontinuity, let's say this is our point C that we're interested in. What happens is that the only issue occurs when x is equal to c. Notice at that point there's no function value. Or if there is a function value, I could also have a situation where the function value is just defined to be elsewhere. What you can imagine is that point at C where it should have been based on the behavior near it was picked up and placed somewhere else or just thrown out entirely. So in this case, what is true about this function? The limit exists. In fact, if we look at the limit as x gets closer and closer to c, we see the output values are getting closer and closer to 1, so our limit equals 1. The function has a value at c, it is 2, but we see that these two things are not equal. So if the limit exists but it's not equal to the function value, then it has a removable discontinuity. Now our next type of discontinuity is where at a certain point, our input value c, the function values before and after are in a large disagreement. Before they're somewhere down here, and after they're somewhere distinctly different. You can imagine that we had to jump to get to the next point. And what this means in terms of our definition of continuous based on the limits and the function value is the main idea is the left hand and the right hand limits at C do not agree. And we know if the left and right hand limits at C do not agree, then the overall function value does not exist. We see the limit as we approach from the left here is about 1.5 negative, and that's not equal to the function value as we approach from the right, which is about positive 1.5. So our conclusion is that the limit from both directions doesn't exist, and if the limit doesn't exist, then we can't compare it to the function value. So that's the idea of a jump discontinuity. We could also have an infinite discontinuity. So in this case, we'd have some type of vertical asymptote through our point x equals c. So if either side of the function as x goes to c is approaching positive or negative infinity, then there's an infinite discontinuity. And for our particular example that I drew, take a moment to evaluate these two limits. As x gets closer to c from the left, we see the output values are getting higher and higher along the asymptote, and there's going to be no stop to that. So since they're getting higher and higher, we would say the limit is positive infinity. As x gets closer to c through the right, we see the output values are getting smaller and smaller without a limit. So that's going towards negative infinity. Since these are in disagreement, the one-sided limits, we know for sure that the two-sided limit does not exist. And one other note, even if they had been in agreement, so this is our C, the two-sided limit still technically does not exist. In this case, we'd say the limit as x goes to c of the function, since they're both going to positive infinity, is infinity. And keep in mind that even though we say it's equal to something, this is a form of not existing. We're just being clear it does not exist because it's going to infinity. So even if they're in agreement and the two-sided limit has a fixed or an agreement point of infinity in this example, this is still a form of not existing because it's becoming infinite. It's not a finite value. Now, the key thing about continuous functions is we know for every point that it's continuous, the limit which can take time to determine, is just equal to the function value if our function's continuous. At the point. Now, if a function happens to be continuous at all points in its domain, then we just call it a continuous function, and we don't have to say where, it's just implied at every point of the domain. So let's think about this. We're told that sine of x and cosine of x are continuous on the real line. So what if we asked about the limit as x goes to 0 of cosine of x? One thing we could do is we could draw a graph, or we can make a well-made table to determine that value. But since we know this is continuous, that's what we were told here. Since it's continuous, doesn't it have to abide by this definition? So it's saying it is continuous here. So shouldn't this be true? The limit equals the function value. So this should be equal to just cosine of 0. And keep in mind this can only occur whenever the function is known to be continuous at that point, because otherwise we can't assume the limit and the function value agree. But since the very definition of a continuous function is that they do agree, if we know a function is continuous, then evaluating the limit becomes as quick as just evaluating the function. So because of this important understanding and shortcut in evaluating limits, it would be helpful to know some of the basic continuous functions, which I have listed here. X to the 1 over n is continuous if n is a natural number, so any nth root is continuous on its domain. Sine of x and cosine of x are continuous. The exponential function b to the x is continuous under these constraints for b. The logarithm is continuous under these constraints. Any polynomial is continuous on the real line. The absolute value of x is continuous. And then rational functions, which rational functions are polynomial divided by polynomial, those are continuous on their domain. And earlier in the class we learned how to find the domains of these rational functions. So with these key families of continuous functions, we can understand when the limit is equal to its function value, if we know that it's continuous. So we know that if a function is continuous, or if the function value equals the limit, then that's equivalent to saying it's continuous. So what if we had a function that was known to be continuous for every point of its domain? What could you quickly tell me about the limit of the function f of x as x goes to c? So c is definitely some point in its domain. Take a moment and pause the video if needed to give yourself time to think about this, and then unpause when you're ready. What we could say is, since it's continuous, we were told it's continuous. Then by definition, the limit is not able to equal whatever it wants. It has to equal the function value. So our limit must be equal to the function value if it's continuous. And this brings us to the idea of the substitution method, which is a quick way to evaluate limits. If the function is known to be continuous either at that point or over its whole domain. What the substitution method says is, if a function is known to be continuous at a point, then by definition we know that the limit is equal to the function value. Or, expressed in terms of symbols, the limit at x equals c of f of x equals the function value. And we keep in mind that this is only possible if you know the function is continuous. If you don't know that it's continuous, you can't make this type of claim. The function value and limit do not have to be equal. So if we know which functions are continuous, and we did list some of them in our previous page of notes, and we know their domain, we can use the substitution method to quickly evaluate limits. So let's determine why this function is discontinuous at a equal to 5/2. So it's telling us why is it discontinuous. Well, first of all, let's plug in the value, because the first step of showing if it's continuous is seeing, does the function value exist? So everywhere there's an x, we plug in a 5/2. 5 times 5/2 would be, and here I just recognized a small typo. If we would correct this, this was supposed to be 2/5. So I meant to originally type that as a as 2/5. So let's make that correction and then continue. So our point is 2/5. Then at 2/5, 5 times 2/5 cancels each other out and we just get 2 minus 2. And we get ln of 0. Now ln of 0, if we think about our natural log function, we know at 0 there is no value, right? Because it's approaching that vertical asymptote for natural log. So this does not exist. And if the function value doesn't exist, then we can't try to entertain whether the limit exists either. So at this point, we can't even check step 2 and 3. So since f of 2/5 does not exist, the function is discontinuous. At a equals 2/5. Because all three things have to be true for it to be continuous at a point.